Good morning, everyone, and welcome to the EuroCase Conference 2021, hosted by the UK's Royal Academy of Engineering. This year's theme is Engineering to Build Back Better. My name is Yasmin Ali, and I'm delighted to be joining you as your host for the next 2 days. I'm a chemical engineer by background, and I now work as an Innovation Programme Manager in the UK's Government Department for Business, Energy and Industrial Strategy. My role is to support technical solutions to help us get to net zero by 2050. I'm excited to join this event as we explore how the engineering profession can help us build a more sustainable and resilient future. Over the next 2 days, we'll be joined by some of the best researchers and engineering professionals from across the UK and Europe who will share ideas, expertise and experience, and we'll explore how the engineering community can play their role in helping Europe to build back better. We're really delighted to have so many of you joining us in this virtual environment, and we hope that you'll enjoy the opportunity to engage with our speakers and the other attendees through our panel and breakout discussion sessions. I would like to encourage you to join in, so do ask lots of questions and engage with us as much as you can. Before we begin, I've got some general housekeeping to go through. Throughout the conference, if you would like to ask questions to the panel, just type your questions into the Q&A box, which is below the live stream, and click send. If you see a question that you like that someone else has asked, then you can upvote it and that will bring it to the top of my screen. So I'll make sure to capture all of those questions. The other point to make is that the recordings will be made available on the Academy and the EuroCase websites after the event. Once the recordings have been published, we will send the viewing links to all attendees, so you'll be able to watch all of this again if you'd like to. So, to formally open our conference, I would like to introduce Professor Sir Jim McDonald, the President of the UK's Royal Academy of Engineering, followed by Professor Tu Lethierry, the President of EuroCase.
Dear friends and colleagues, on behalf of the UK's Royal Academy of Engineering, I'm delighted to welcome you to this year's annual conference of EuroCase, the European Council of Academies of Applied Sciences, Technologies and Engineering. This year's conference focuses on the theme of engineering to build back better. And the phrase build back better has indeed been used extensively in recent times, and arguably perhaps it's even been overused. However, there is no doubt that the events of the past 18 months have given us an opportunity to take stock and consider whether we are indeed on track to build a society that is increasingly sustainable, resilient and inclusive. This EuroCase conference will help us consider the role that our community of European engineers, researchers and innovators can play in delivering this future. These themes are central to our Academy's goal to harness the power of engineering for a sustainable society and inclusive economy. I'm delighted that over the next 2 days, we will have the opportunity to share some of our Academy's work in these areas, from our Net Zero Engineering Policy Advice to our Engineering X Safer Complex Systems programme, and of course, to have the opportunity to hear and learn from the innovative work going on across Europe. We are incredibly conscious that these challenges go beyond national borders and that international collaboration, particularly in research and innovation, will be essential in tackling them. As the UK engineering community, we are strongly committed to continuing to build strong and fruitful partnerships with our European colleagues as we seek to build a more sustainable, resilient and inclusive future. EuroCase has an enormously important role to play, bringing together the engineering community across Europe and providing them with a strong voice and route to inform and engage with policymakers on these key themes. I'm sure that this event will be an excellent opportunity to share experience, expertise and ideas across the European engineering community as we collectively seek to build back better. And I also look forward to seeing the outputs from what I know will be a highly relevant and stimulating conference. Thank you.
Thank you, Sir Jim, and thank you very much, Royal Academy of Engineering. And also welcome on my behalf to the 2021 annual conference of EuroCase, this time focusing on the theme Building Back Better. And building back we need indeed after the pandemic, which has challenged the entire world, but also taught us to use digital channels for the meetings as we are doing today. Clearly we want to and need to meet in person, but these digital means also allow us to meet more often in a sustainable fashion to manage our day-to-day business, especially vitalizing our international collaborations. The COP26 meeting aiming to unite the world to tackle the climate change has only just finished, so we can now start to assess whether such a commitment was reached. And I would say not yet. There are still gaps between countries that are behind the net zero agenda and will take action, those that are delaying the agenda and those that will be the first to suffer the consequences of delaying the agenda. So it is of course disappointing that India, among other countries, in the very last moment managed to change the wording from phase out to phase down of coal and fossil fuel subsidies. There will be consequences for this decision. Some of the other decisions, though, of the COP26 are historical, and they're demonstrating increasing awareness of the urgency of the actions that are needed. The decisions that focus on research, education and innovation to tackle the climate change are particularly relevant for the engineering academies and engineering communities. It is in those areas where engineering academies can make a difference by providing independent advice to governments on what type of actions are likely to lead to workable solutions. And the academies also have an important role in explaining why engineering and new technology are so crucial to the global response to the climate change, or the crisis, as we should say. And due to our strong networks of engineering academies all over the world, we can and must also promote inclusive innovation. These grand challenges only can be won by collaborations across all borders. All regions of the world really need to be part of the solutions. So our academies represent high level of expertise in the member countries and can contribute to sustainable development by sharing knowledge and expertise worldwide. We can contribute significantly to translating the ambitions and decisions of, for example, COP26 into action, building back better, as we say here today. So I want to once more thank Royal Academy of Engineering for excellent job in shaping the current program and by inviting us all to nominate speakers, as we say, all over Europe. I do want to highlight the importance of the EuroCase conference as an international forum for sharing insights and inspiration, and an excellent opportunity for us to come together as proud Europeans. Thank you very much.
Thank you so much to both Sir Jim and Professor Thierry for welcoming us all so warmly to today's event. I'd also like to take this opportunity to briefly introduce our event co-chairs. So that is Professor Adisa Azapagic and Professor Rick Parker. So over to you, Adisa.
A warm welcome from me as a co-chair of this EuroCase hosted by the Royal Academy of Engineering. I hope you'll agree with me that this is a very exciting time for engineers and engineering, with many opportunities to build back better. I hope that the conference program both reflects that excitement and will provide a stimulating environment to discuss how we as engineers can work together with other disciplines and professions towards a more sustainable future. I wish you a very successful and enjoyable conference. And just before I hand over to my co-chair to welcome you, let me thank Nicola and the team at the Academy for their excellent work on making this conference happen. Thank you.
So let me finally add my welcome. It's a great pleasure to have you all here, and I'm just sorry we couldn't physically get together for what's always a great event in my calendar, the EuroCase conference. I'm a treasurer of EuroCase, so I look after the bookkeeping for them, and it's been great fun pulling this conference together. We have a fantastic list of speakers, as Tula said, from all parts of Europe, and addressing three major topics for society, not just for engineering, over the next day and a half. So I hope you enjoy it, and like my co-chair, I will just add my thanks to the fantastic staff at the Academy who've done so much to pull this together. Thank you all.
Many thanks to you both. Now I'm delighted to be able to open our first main session, which will focus on engineering for net zero. With the crucial COP26 conference closing just a couple of weeks ago, this is of course very high on all of our agendas. So it's very timely that our first keynote speaker, Professor Paul Monks, will be telling us more about how the UK plans to deliver its own commitments on net zero, and the importance of the engineering community in meeting these goals. Paul is Chief Scientific Advisor to the UK's Department for Business, Energy and Industrial Strategy, so the same department that I work for. And prior to this, he was the Pro Vice Chancellor at the University of Leicester, where he remains a Professor of Atmospheric Chemistry and Earth Observation Science. Over to you, Paul.
Thank you, Yasmin, for that kind introduction, and thank you for inviting me to come along today to discuss this. So if I could have my slides, I'm going to help hopefully frame this session for you. It's called, these slides, Engineering Net Zero, Engineering and Net Zero. I mean, actually, it's an interesting title. Is it engineering and net zero, or are we engineering net zero? For me, actually, as we go through this talk, I think we'll find there is a critical difference for that, and we actually, and the engineering profession and science behind that needs to step up to engineer net zero. It's a critical part of this. Next slide, please. So what is net zero? Just before we kind of get into the lingo, it has a particular meaning. It also has a very different meaning in different countries, and I recognise that you know, there's a range of countries on here. In the UK, we commit to being net zero with respect to greenhouse gas emissions by 2050 compared to 1990 levels. So that's 100% reduction by 1990. And we use a set of different mechanisms to do that, which are actually set in UK law, in the Climate Change Act. But that also is the same mechanism that we use internationally to publish our nationally determined contributions, which is what was to announce recently at the COP26 conference, where all the countries of the world come forward and commit to reducing their greenhouse gas emissions. So for us, it's a seamless process that embraces that. Next slide, please. So how do we achieve net zero? What are the ways? And there's a figure on the right there looks at the abatement pathways in terms of reduction in equivalents of carbon dioxide, and the different colours there are the different ways that we're thinking in the UK that we are doing that. And this begins to talk to the heart of engineering net zero, because actually, you know, we need to reduce demand. Yeah, we kind of forget about this, and we're going to talk a lot in a minute. I'm going to start about talking about how you decarbonize the energy system and the like. But actually, if we can reduce demand or improve efficiency, then we don't need to create the energy in the first place. And that's going to be a really important element for going forward. And it's a real challenge to the engineering world to, can we reduce those energy demands? Can we improve the efficiency of the way that we use energy, but also the way that we use products and services as well, making them more recyclable and the like. So it's efficiency in all the ways that we use energy, either literally or embedded energy in products and services as well as then the drive towards low carbon solutions, electrification, hydrogen, carbon capture and storage, as well as generation of greater amounts of low carbon energy. And remember that a number of our emissions come from land use, and we're going to be able to have to look at land use and greenhouse gas recovery elements, maybe negative emissions as well, as part of that future of net zero. But there are different pathways, and different countries will have different pathways, and it's important that it's always understood in that context. Next slide, please. It's a systems problem, and I think it's worth remembering. And whenever I say it's a systems problem, engineers always step forward and say, actually, we are the systems thinkers. And I think there is absolute degree of truth about that. But it is a systems problem. Here again, I've just done the energy transition, going for the main energy sources, the main usage sectors on the right-hand side there, and a number of the system linkages there. But you'll notice the systems of systems problem, because that sits in a global energy transition as well as a country-based energy transition. But it also sits in other systems. It sits in the economic and financial systems, which will drive this, either in the country level financial systems and funding, or also the global economy and the global economic system, which was all very much the fore in COP26 and the second key goal of COP26. So we've got the energy transition, we've got the financial system, but also we've got consumer behaviour and behaviour change as part of that, people in that system as well. So it's a really genuine systems of systems problem, net zero. And often the challenge of talking about policy in this is actually this interconnection and these systems. And engineers are in a peculiarly good place actually to be able to talk to policymakers because of your understanding about systems and systems thinking and the ability to do that. Next slide, please. So it's worth recognising when we talk about net zero that actually it's going to require an economy-wide transformation. And here I've listed the major emission sectors in the UK economy, but actually they would be true of virtually any wider economy, looking at transport, business, power, land use, buildings, as well as some of the negative emission technologies that we're going to use. So when we talk about net zero and the net zero transition, it's going to require an economy-wide transformation. There is not any part of the economy that will not be touched by the transition to net zero. Next slide, please. But it's also remembering, and it's very easy as engineers and scientists like ourselves to become too technocratic about this, and to think that actually, it can all be achieved with technology, and it's not. It's going to be, people use technology, and also it's the way that people use that technology that is going to be critical to decarbonising the economies of Europe and the world. And we've got to think a little bit about how those link together, in particular around things like healthy diets, aviation, and also, as I said earlier, engineering products that last longer, use less resources and the like. So actually it's important to think about all the different elements of the net zero transition, and not just think about it as a mitigation problem. It's a mitigation and adaptation problem, but also it's not just a mitigation problem that's driven by technology. It's a mitigation problem that's also driven by people, and behavioural change being a key element of that. And that has to be engineered into that low carbon future that we're designing. Next slide, please. So how do we achieve net zero? And if you go to a government context, and how do engineers and scientists influence that? In the UK, what we've done is we've got a series of strategies that we've put together just before COP26. And if you're interested, it's really worth a read, all 176 pages of it, about our net zero strategy, which is called, similarly to this, Build Back Greener in some senses. And also we have a 10-point plan for a green industrial revolution that really shows the major goals in terms of decarbonising the energy system and the transport systems that are going forward. But it's these strategies and the way that science and engineering underpin these strategies which are a key element of our vision for that, and our way of achieving that. It sets out the ambition and begins to think about the way that you can deliver that on the sort of timescales. And 2030 is a key decade for that. We need action now. If you look at any of that, we've only got a small amount of the carbon budget left. So it's not also with technology and systems thinking. It's not about pushing it into the future. It's thinking about solutions that roll from now out to the future as well. Next slide, please. Just to kind of give you some framing of the scale of this challenge, this is a slide of UK energy demand over the last few years from colleagues at the University of Birmingham. At the bottom, you've got the electrical demand. In the middle there, you've got the amount of energy that's used in fuels. And on the top of that is the UK use of gas. And you can see that we're nearly using 4,000 gigawatt hours in there. And if you think about it, the future is no gas. Much of that liquid fuel will be electric. And you can see that we're going to really have to be able to double our electricity, low carbon electricity generation by 2050. And you can see, therefore, the absolute scale of the engineering and science challenge ahead of us. When we're getting nearly to 5,000 gigawatt hours of electricity, it's going to be a real challenge. And I always think this is a very salient slide to look at, to kind of remind yourself of where we have to get to. We're not messing around on the edges here. We are economy-wide transformation. We are going to have to make really big changes. Next slide, please. And if you look at that journey to net zero, and I've taken these figures from our strategy, on the left here is the 2019 energy sources and end uses of those, and those sectors that I've talked about, and the way that you can see the dominance of the fossil fuels in that. On the right-hand side there, you can see in the high electrification scenario, still the same usage sectors, but now the way that we're a pathway to achieving that high amount of renewables, bioenergy sources becoming more dominant, and if we're still using fossil fuel sources, those being abated with CCS or negative emission technologies as well. So that's a future that is quite strong, and it's also a future that presents a range of engineering challenges, not only in the scale of energy production, but in energy storage, in energy distribution in a system that has high intermittency. So there's a whole number of engineering and science challenges that underpin what are these broad brush approaches to net zero. And we need that, and policymakers are going to need that understanding to be able to deliver these sort of outcomes. Next slide, please. So how do we do that? How do we do research and innovation to do that? As part of the UK's net zero strategy, we produced a research and innovation framework. It makes, not surprisingly, the push that we've got to have to do a whole systems approach to this. The transformation is going to be quite large, and we need that integrated systems approach. But again, you can see the wheel on the right-hand side. You can see many of the technologies that I've already talked about. You can see the socio-economic insights that are going to drive those technology suites, and that you've got the different sectors there. Again, you've got the different technologies that contribute to that. But also, you'll see there's the enablers. Data and interoperability, the digital revolution is, digital net zero is going to be important. And that's not just about decarbonising mainframes. It's about the way that we use the data to be more intelligent about how we use energy and resources. Finance, in order to deliver that. Policy, the levers to change that research and innovation thing, the skills of people and skilled people. We're going to have to change the way and the skills of the people that we've got in order to be able to deliver that, as well as an understanding of the end users and the people that will use these technologies. The point is, again, that people use technologies. It is an important part of that, and you can't take people out of that system. But that's a really good framework that brings together the sort of challenges, but also the enablers for that decarbonisation, and the central role that research and innovation in both science and engineering will make in order to deliver that. Next slide, please. If we think about science and net zero, there is no greater challenge for me. We've got to make net zero sustainable, we've got to make it resilient, and I think we've got to make it measurable. Engineering will help us with sustainability. We've got to make it resilient to its mitigation and adaptation, not one or the other. And we've got to make it measurable and real to people. Next slide, please. So COP26 in the international context of this. Next slide, please. COP26 has a wide range of outcomes. I think I would note that science has never been more to the fore than in the recent COP26. We had a Science and Innovation Day. We had science at the top of the agenda with respect to the documents that were produced. Science was threaded through everything that COP26 does, and that bringing the international countries together. So international collaboration, like we're talking about today in this Eurocase conference, is really important. And you can see some of the major impacts that came out of COP26. Was it enough? No, we always have to keep pressure on. Every fraction of a degree counts. We've got to keep moving forward on this agenda, and science and engineering will enable us to do that. Next slide, please. International collaboration is absolutely essential for that. I think COP26, if it leaves you with anything else, this is a global problem. We're all in it, and we will not be through it until we're all through it in some senses. Both the EU and the UK work together to put some plans together in terms of the COP26 Glasgow Climate Pact and the EU's Fit for 55 package, which was a very strong set of measures around that. And both the G7 and the G20, which are going to have things like the Clean Energy Ministerial and international partnerships for hydrogen and fuel cell economies, are going to be part of that as we move forward. Next slide, please. Engineering is going to be essential to delivering that. Next slide, please. And I took from the Royal Academy of Engineering's recent report of rapid, low regrets decision making for net zero policy. To deliver net zero, we need to start thinking like engineers. To make it a success, we need to stop modelling and start building. So I'm not an engineer, I'm a chemist by training, but I leave that challenge maybe to the panel to kind of pick up as part of this. But you'll notice it's that concurrent coordinated transformation, it's that systems thinking, it's putting the technologies that we have today, deploying those at scale, as well as the technologies for tomorrow. And the engineering community is in some senses, an absolutely ideal place to be able to think about how to deliver that range of visions that is going to be essential to decarbonising our global economies. Next step, please. Next slide, please. So some take homes from this. It's a significant challenge. It's pervasive, net zero. Systems approach is going to be an incredibly important part of that, and behaviour change is as well. And really, engineering, science, and innovation is absolutely critical to those net zeros, and we need to do that in a framework of resilience and sustainability for the future. Next slide, please. And if you want to follow me on Twitter, that's an unashamed plug at the end of my talk, please follow me on Twitter. I tweet a lot about the issues around that and the science policy issues and science and engineering policies around delivering that. We can go back up a slide, please. So hopefully you've enjoyed my short talk and my short introduction. Hopefully I've framed to you the challenge of net zero and the role that engineering and systems thinking can play in delivering that. Thank you very much indeed.
Thank you so much for that, Paul. That was a great start to the day, and I'm sure we will explore many of those themes a lot further during the session. So I'm sure you've all got views on the outcomes of COP26 and the plans and commitments. So before we kick off with our first panel session, we've got a little bit of time for a quick audience poll to gauge our position as an engineering community on this topic. The question that we've got for you today is, in your opinion, are the commitments made at COP26 option A, achievable with the national plans and strategies currently in place? Option B, achievable if national plans continue to be developed at pace? Option C, achievable only with more significant changes in how we develop and implement policy in this field? Or the final option is unachievable within our current systems. So the poll should be available below the live stream for you to select your answer. So have a think. I can see some people are already starting to respond. While you respond, we've got a short video to introduce this topic further. And I'm sure that you'll notice the echo of many of the key points that we've just heard from Professor Monks. So let's take a look at that video now.
In 2019, the British government committed the UK to achieving net zero greenhouse gas emissions by 2050. Over 130 countries around the world have pledged to hit the same target. It's a highly ambitious deadline, and it needs to be. Delaying action on emissions risks runaway climate change. At the same time, choices we make now will live with us for decades or centuries to come. It is important we act now, and it is important we get this right. This series of video explainers will explore how we navigate our way through an increasingly complex and connected modern world to reach net zero, in line with the Paris Agreement. We call this joined-up process a system transition, and it's how we get to net zero. Nicholas Stern is a former chief economist of the World Bank, who hit the headlines in 2006 when his Stern Review on the Economics of Climate Change was published. The 700-page report laid out in stark terms the devastating economic toll that climate change would have on the global economy if left unchecked, and stressed the economic benefits of early intervention. 15 years later, net zero remains at the top of Stern's agenda.
If we're going to stop temperatures rising, we've got to go to net zero. And to get to net zero emissions, we have to radically change in real time, just 2 or 3 decades, the way we run our economies, and that first decade will be absolutely decisive. But when we look at that challenge, actually we will be discovering and creating a new form of economic development, much cleaner, much healthier, much safer, and much more productive than has gone before.
But government setting an audacious goal is one thing. Making it a reality is a far bigger challenge.
We have really the biggest transformation the world has probably seen in a peacetime economy, with enormous progress required this decade. But you've got to invest to get there, you've got to change quickly, you've got to manage that change, changing in the very big systems of cities, energy, transport, land, and of course a big change in the overall system of the way the economy functions.
Achieving net zero is a massive systems challenge. It's going to involve simultaneous transformation of a whole range of vital and interconnected infrastructure systems, from transport and housing to energy and manufacturing. So we absolutely have to take a systems view to understand interdependencies between those different components of a system, understand where the trade-offs are that we're going to have to make, opportunities for leverage and incentivising the right behaviours so that we can align all these different factors towards this singular outcome of net zero.
A systems perspective shows us the crucial connections between the systems upon which we depend. Infrastructure systems around the globe rely on natural resources and ecosystems for their materials, energy, and safe operating conditions. In turn, our infrastructure systems depend on and support each other, so when we make a change to decarbonise our transport system, it also changes what we need from our energy system and from our built environment, and vice versa. Making good decisions for any of these, and especially making decisions that protect the ecosystems they rely on, requires a strategy for all of them.
Without a framework for joined-up policymaking, finite resources such as zero carbon electricity supply or the rare metals that we need for key technologies such as batteries are not going to be available when and where we need them. So we end up in a position where we could be in this macabre version of whack-a-mole, where we reduce emissions in one place and then they pop up somewhere else in the economy or perhaps in another country. We deploy new technology but we don't have the right structures in place to get the benefit. You can end up creating more problems than you solve.
Engineers are often the people building, operating and integrating all the parts of these different systems: transport, energy and buildings. Engineering skills and systems thinking are needed to bring them together to create a net zero future that works.
Engineers are innovators, problem solvers, systems thinkers. They're fundamental to fully realising net zero anywhere in the world. And the systems approach is really core to engineering. It's what we sometimes call one of the engineering habits of mind. And it provides us with this structured, disciplined approach to managing complexity. It's like a toolkit that we can use. Engineers can also use systems approaches to handle less tangible products and to help us cope better with uncertainty. So it's really important to remember that when we talk about systems, we mean socio-technical systems. We need to think about how systems work in the real world, interacting with people and planet.
Implementing net zero is an unprecedented and all-encompassing challenge of delivery and integration. Engineers will need to collaborate with other disciplines, policymakers, and crucially the public to guide the transition in a sustainable and just way for all.
It's a combination of science, engineering, public policy, city planning, town and country planning. It all has to be put together. So you need the systems engineers of the really technical system engineering kind, because these are complicated engineering systems. But at the same time, you need the systemic side, society, economy, government to make this happen. And the government side is critical.
Before we go into those themes further with our panel discussion, let's have a quick look at the poll results. So that's interesting to see. Most of you think that this is achievable, but we need more significant changes in how we develop and implement policy in this field. So I think it's good to see that we all recognise the challenge, but I think there is quite a lot of optimism needed to help us to get there. So it's good to see that people haven't given up already and decided that this is not achievable. So we'll probably pick up a bit on that during the session. So let's get started. I'm going to introduce all of our panel members for this morning. We've got Professor Becky Lunn, who is a research chair in biomineral technologies for ground engineering at the University of Strathclyde and a member of the National Engineering Policy Centre's Net Zero Working Group. Our second speaker is Professor Peter Lund. He's the Professor of Engineering Physics and Advanced Energy Systems at Aalto University and co-chair of the recent SAPEA report, a systemic approach to the energy transition in Europe. We've also got Professor Christoph Schmidt, President of RWI, the Leibniz Institute for Economic Research, and co-chair of the SAPEA report along with Peter. And our fourth speaker today is Yves Bamberger, former Director of R&D at EDF, a Fellow of the French National Academy of Technology, and chair of the CATES Energy Committee. So I'm going to kick off by giving each of our speakers 3 minutes or so to introduce their perspective on our topic. And just a word of warning, I may cut you off if you're going over the time, just to make sure that we have enough time for discussion and questions at the end. So let's kick off with Becky, please.
So good morning and thank you for inviting me. It's great to be here. So I'm going to reinforce a few of the points that Paul has made, I think, to start. So in order to meet the challenge of net zero, we need to manage a transition to a low carbon energy system in particular, and that's a huge challenge. So at the moment, renewable electricity accounts for around 20% of total energy consumption. That's even in Scotland, where we have quite a high percentage of renewables for electricity, but we have a large heat demand. But in all of the UK, it's very low. So we have nuclear that can add to low carbon energy, but has long lead-in times, and we need to increase that low carbon generating capacity substantially. And as Paul said, at least double it, 2 to 3 times that capacity. And we also, whilst doing that, need to remove our built-in reliance on hydrocarbons. So some of our technologies, it's not easy to decarbonise and suddenly to transfer over to renewable electricity. We need to reduce our burning of natural gas for heating, and we need to move over from petrol cars to electrified systems. Those two between them account for 75% of our current energy use, and that has to change. So even if we increase low carbon generating capacity by 2 to 3 times, we're still going to need to reduce energy demand by at least 50%. So we need to halve at least our energy demand to meet this challenge, and that's a real challenge. So we need to look at how we use energy in buildings and reduce that, and we need to think about products. At the moment, our economy relies on us buying more and more things. That's a successful business. That has to change. So we need to be reusing and recycling materials in products, using less of them. So where do engineers come into all of this? So engineers, as everybody has said, are experts at managing complex systems. And just to give you one more sort of concrete example, if you like, let's think about decarbonising homes. So we need to reduce heat loss in housing and the demand that homes make. It's a very large part of our current consumption of energy. If you take Glasgow City Council's targets, if you divide the target by the number of homes, it's already, if we start today, retrofitting one home every 19 minutes, which is an enormous rate of retrofit and clearly can't be done by one engineering company. So we're going to require a very large skilled workforce that we need to build up and train very rapidly, but that's not enough. We need volumes of materials in ready supply, so we need insulating materials. Some of those might require some more development as they tend to be hydrocarbon based, so we may need new insulating materials at pace. We need glass, we need PVC, which is currently in shortage, in order to put in glazing and improve double and triple glazing. We need transport capacity for those materials throughout the UK and beyond. We need economic policy drivers. We've got to accelerate a new business really rapidly, so that will require policy drivers, it will require regulation, and it will require new certification schemes to guarantee quality of the job. And also, critically, we need carbon certification schemes, particularly on materials which are mined. They have huge energy inputs themselves. We need to change that process. So we need to be able to guarantee that the materials we buy for this have a low embodied carbon in the future. Currently, there's no way of doing that. So just to sort of sum up, engineers are experts at managing these kinds of complex systems. We need to map those systems out, find the pinch points, and act in a timely way to make sure that we don't set one thing off and then find we can't complete it because something else pops up the back that doesn't allow it. And that sort of thinking can also identify where the really critical and urgent research and development needs are. So, thank you.
Thank you very much, Becky. Let's go to Peter next, please.
Okay, thank you very much for the kind invitation to be here today. In my short talk, I would take a perspective from the SAPEA report, and those who don't know what SAPEA stands for, SAPEA is the Science Advice for Policy by European Academies project, run by 5 major academies in Europe, being part of the science advice mechanisms. The SAPEA Working Group on Energy provided a report on a systemic approach to the energy transition in Europe just recently, and clearly indicated that we need to consider concurrently 3 major elements in order to be successful one in the energy transition. Naturally, technology is one of the core elements indeed, and important for the transition, but you need policies and you need proper regulatory mechanisms to pull the technologies into the market. And thirdly, and I think is increasingly important, and we already heard today, are the social dimensions of the transition. This transition, taking its magnitude, is a huge socio-technical transition, which touches everyone in Europe and on the globe actually, and that's why the social dimensions, being for instance the social behavior or social acceptance, or in some way coordinating the millions and millions of decisions that we need for clean energy as an example, or that those elements will be extremely important. So this trinity, technology, policy, regulation, and social dimensions, this is like a clockwork, and the different elements are the gears, and as you realize, the clock don't move forward if the gears are not synchronized. This synchronization of these 3 elements, so that the clock moves forward, transition moves forward, that actually is one of the core issues of the systemic change that we need, and that's of course the major challenge that we have here. SAPEA in its report touches many of the elements of the systemic approach, and if I look just on some of the technology issues that we have in front of us because of the major technology changes that we have, is that we see, for instance, that the energy system, which is now almost completely fuel-based, will change in a few decades into a weather-dependent, data-dependent, material-dependent energy system, which is a huge challenge for engineers indeed to master. We think this issue of energy system change, the questions of integration and system aspects just on the technology level will be very important. So from an engineering point of view, it will definitely be important that engineers will be able to be one of the gears in the clock, and we understand the different disciplines. We understand the social issues and the adaptation with social aspect that we need to look on. but we also need to link ourselves to the regulatory framework that exists. In that sense, I think engineering can be very, very successful one. But to be concrete, what kind of questions do engineers typically provide answers to? Well, very important question is what is possible? What can we do? What cannot we do is very important. And maybe for the future, what can we do? So these very fundamental questions, which I think policymakers will need when they do decisions, who else than the engineers could provide? So with this word, I hand back to you, Jasmine. Thank you.
Thank you very much, Peter. Christoph, over to you.
Thank you very much. Thank you for the invitation to provide insights from the discipline of economics and from the social science more generally into the question of how we should be able to put sustainability and net zero at the heart of economic growth and economic recovery across Europe. I think there are two elements to be discussed. One is the conceptual prerequisites, the principles to follow. And the other element is to draw concrete conclusions from this. Let me start with the principles. I think that every speaker so far was in agreement that we need a systemic view, but I want to stress that the particular challenge is not that it's a multitude of interactions that we have to observe, that it's an extraordinarily dynamic system that we are observing and analyzing, but it is inhabited by a multitude, a myriad of actors, households and enterprises who follow their own objectives, their own preferences and constraints. They have their own will. So understanding their decisions and framing the environment in which they take these decisions is mostly important. So it's a socio-technical system with objects forming that system, combining into that system, which have their own will. So policymakers cannot follow a detailed plan. They must humbly set a frame for private action in a learning system. That was one prerequisite. The other prerequisite is the global ambition. All European progress is ultimately futile if it does not effectively lead to mitigating climate change on a global scale, and we cannot do it on our own. So policymakers need to administer a European transition towards climate neutrality, which incentivizes sufficiently many other nations to follow suit. What does it mean in the concrete? Well, the policy package that's providing the frame for individual actions needs to be holistic and encompassing and internally consistent. And it needs to fulfill several requirements that we address in the SAPEA report quite clearly. It needs to be effective. That's no contest, actually. Nobody will follow you if you don't fulfill your own objectives. But it also needs to be efficient. It needs to avoid wasting economic resources, because if you pay more for defossilization than you need to, if you waste economic resources, they are not available to other uses. And the guiding policy instrument that we identified is carbon pricing. Of course, augmented by the right things, by infrastructure investments that make the carbon price unfold fully to its full extent. But carbon pricing needs to be in the middle. And of course, engineering is helping everybody or the whole system to lower that cost by technical progress. No contest about this, but it's a socio-technical issue. And that leads to two more requirements. The transition needs to be socially balanced, because all climate policy is in itself regressive, in the sense that low-income households use more of their budgets for energy sources. So making energy more expensive, which is the way to go, either by price measures or non-price measures, it will cost economic resources. This is regressive. So we need to compensate low-income households. We need to engage them in participation schemes to preserve the acceptance. And finally, we cannot risk to lose our own prosperity in the process. Carbon leakage will not help anybody, because the climate will not be helped. And loss of prosperity means nobody will follow you whose own prosperity is still to develop. So we need climate alliances, we need the global alliance, and that is something that is the second requirement. Systemic view is fine, but it needs to be a globally systemic view.
Thank you very much. And last but not least, over to Yves, please.
Thanks. Hello, everybody. I'm really happy to be here with you. I will look at from another point of view. We say all engineers are important, but it would be better if the other citizens and policymakers say that. It means I will shortly speak about the magic triangle, engineering, policymakers, and society. I think we don't have to forget that the trust in engineering and science has decreased, and I'm not sure that the outbreak is increasing. I think it's exactly the contrary. We have to work on the trust that policymakers and society may give us. And for that, we have to be very clear and to be very modest, saying what is known, uncertain, what is not known. I would say saying the light and describing the lights and shadows of technologies, how it's done in Kyoto every year at the STS Forum. That it was my first point. My second point is that we speak always on innovation. We never mention progress. For people, innovation is somehow often relatively boring, but progress is good. And I think we have to remain to everybody what has been done through engineering, technology, and science these last 100 years. And I was listening, all of you, only Sir Stern was mentioning progress. You never mentioned progress. I think we have to mention again progress to show the policymakers and the citizens that engineering and science are bringing progress. And last point, I think also we have to address the ethical questions. Pushing energy efficiency first, I think, is not exactly the same than pushing low carbon or low emission first. And I think to be inclusive, to think to poor people in cities or in emerging countries, saying energy reduction, that it's not acceptable. Even more, if we think again that all is limited on our planet, but energy is not limited because the sun is sending us 8,000 more energy that we need. So the question is decoupling energy and energy use and environment and emissions. So I think to summarize, we have to be modest, to be desired, and to make a little last comment, when we see the governments in our Western countries, in European countries, compared to some others, there are very few engineers. It means that perhaps the trust that have policymakers and citizens in us is not so high, and it has to be higher in the future. And I hope we will succeed to do that. Thank you.
Thank you so much. Thank you for sticking to the time as well. That's much appreciated. I will kick off the discussion with a couple of questions, but I would love to see your questions, all of those audience members who are watching. So submit them via the Q&A that's at the bottom of your screen. I think quite a few of you mentioned the importance of behaviour change, and I think as engineers, it's probably not something we're taught about that often. So what do you think the role of engineers is in that behaviour change side of things? Maybe I'll start with Becky, if that's okay.
So actually, I think the role is significant. So people won't change behaviours if that behaviour is difficult or expensive to change. It needs to be something that is, I think there is a will to change. I think there's a real society will to change, but it needs to be possible too. So, you know, there are many places in the UK where public transport, for example, is not an option. and a car is the only option that you're going to have. It may transferring to electric vehicles currently is an expensive option, so it's not something that's available to many people. And if you take Glasgow as an example, most people live in flats, so they don't have the possibility of a home charging point. So we have to think very carefully about what the blocks are. It's all very well asking people to change behaviours, but oftentimes they can't. So we have to think about how to make that feasible, and that's partly engineering and partly policy. A lot of it is policy.
Eve, did you put your hand up? Yes, do you want to come in with?
Yeah, to give a practical example also, when you have some air conditioning system in a car, you could have an automatic system. It means if the air conditioning system is running one day, when you use the car the next day, automatically it's on. That it's a bad solution. You have to impose the people to switch on the air conditioning system when they go in their car, but they are free to switch on or not to switch on. I think that it's a very it's a very little question, very little point, but it helps the people to avoid to use energy and to produce CO2 emissions. That way they are free, but the engineering way help them to reduce the carbon emission. We don't impose them the solution.
Thank you, Eve. Peter, do you want to come in next?
Yes, I think this is a very important question in the sense that behavior will determine if people accept or reject the technology. And in that sense, the role of the engineers would be to make a technology more human-centric, acceptable for people. Take just an example of a large-scale wind power, which cause sometimes problems within the local population, noise problems, etc. Now, what can the engineers do is so far we haven't looked on the solutions, but you could use acoustic materials to reduce the noise. So there's an engineering solution to a grave problem which may hamper the use of wind energy in the future. So I think being aware about these social interactions and having more interaction with the population, ask the customers. Customer is the king always. I think that will be very important. And I think we need also to maybe update our education system. In some engineering schools, I know that they have some social science courses, but maybe in the future we need to have a much stronger, also multidisciplinary kind of education in this respect.
Thanks, Peter. And Christoph.
Yeah, I have quite a different complementary position. Old habits change very slowly. And Peter was indicating that by education you can do a lot, but you have to really wait for a long time to have that work out through the population. Now, economists bring another perspective to the table regarding behavior, namely a reaction to prices and other behavioral changes. So in layman's terms, from an economist point of view, one would speak of behavioral change when people do different things than before. Let's say they use other modes of transport, public transport instead of using their diesel cars, for example. Now, we wouldn't speak of behavioral change as economists if people just followed the alteration of relative prices. So if you put a carbon price on the diesel fuel, and people use more trains instead of their diesel cars because of this, this is the same behavior. You don't need to put any effort into changing people's minds, but you still change their mode of transport. It's more difficult to infuse a sense of responsibility, for example, that says, well, irrespective of the carbon price, I use more trains than my diesel car. One aspect where this becomes really pertinent is the rebound effect. Should we incentivize people by carbon pricing, avoiding the burden of higher prices by using more efficient modes of receiving a service? That would be our suggestion. And we discussed at the SAPEA group very intensely whether efficiency standards could deliver the same behavioral change. And the answer is no. You might think that given the behavior, more efficiency or better efficiency standards mean lower use of fossil fuels. Well, but cheap people understand that the service they receive from this is less expensive, so they demand more of this. So they somehow eat up, they nag. This is nagging off of the original impact. So you need to go to the behavioral sciences to understand behavior. That's our message.
Thank you. And Becky, do you want to make a comment on that?
Yeah, just one brief thing to say is that engineers have a bit of a track record of, and there's a lot of well-publicised track record, I would say, of designing for men. And if we wish behaviour to change, we need to design for a much more diverse population than we currently do. It needs to be easy and the right choice for everybody to make, not just a few.
Thank you. That is a very, very good point. Just picking up on another subject that a couple of you mentioned on carbon pricing, and I hear this a lot, and I wondered if you have views on why we haven't got this yet. So I don't know if someone wants to, maybe Christoph, I don't know if you want to start on that one.
This is really a tough question, actually, since the case to be made for carbon pricing is so clear. We are so rich in the world. We have escaped, in many parts of the world at least, escaped dire poverty that has plagued us for centuries because of the division of labor. And division of labor is labor that is used to produce in different places different things. Everybody is specializing, is working in a market system, and that market system needs a market signal, and that's a price, a uniform price. And the same here. The case for carbon pricing is we could use division of labor to have as little cost as possible for decarbonization. Why isn't it flying? Because it makes transparent how costly the whole affair is. And policymakers, for good reasons, are shying away from complete transparency so far because they hope that non-price measures might be less expensive. But if you look closely, they are not. Typically, they're even more expensive and more socially unbalanced. So more transparency is key.
Does anyone else want to comment on that question? Peter?
Yeah, I think definitely this is one of the key questions that we have for the energy transition. And I have two viewpoints that also came out of the SAPEA report. One is of course that we need a global, let's say preferably a global carbon pricing scheme, and one country or one continent just going alone is not the solution. And you need of course to have mechanisms for a fair solution globally. The second point is of course the question about the justice, in the sense that very often those who are the weakest and poorest in society may actually suffer from raising prices, and we need this socially just mechanisms which compensate for these changes. We have in Europe nowadays 30 to 50 million people who can't afford heating. And I think, and that's why we need to think about carbon pricing also in a socially just frame in Europe and globally, and that is tough, where maybe the richest need to share some of their wealth with the poorest one, which we know is one of the let's say key ethical questions that we may have in this transition.
Thank you, and I'll hand over to Yves for a final comment on this question.
Yeah, briefly to complete what Christoph and Peter were saying, even if we increase many prices and costs to the carbon tax, which will be good, why we don't give back the money to every people equally, to all people, to all citizens in the country, in the different countries? Because finally, that's a question for everybody. Like Christoph was saying, we have all to be active, and to be active, it would be good if we have perhaps many things are more costly, but at the same time we receive money, and we would know how all this money will be used. The money coming from the tax will be used by the government. It would be better to give back to the people. That was my comment.
Thank you, and I'll just, Becky, if you could quickly.
I'll make it brief, but I was just going to say that it's not just about pricing, it's also about accounting. So at the moment, we don't have a unified way of accounting for carbon, and there is no certification scheme. So actually, even if you can afford it and you wish to make a public choice, you can't do it because there's no way of knowing how much carbon is in a product.
Thank you. Okay, I'm going to go to some audience questions. The first one is, does the panel believe that we have the necessary tools and capabilities to effectively manage the extreme complexity levels that we are facing? Who wants to take that one first? Becky.
Go on, I'll have a go. So I think we do, but I think we just have to get on with it. So we will make mistakes. It's absolutely inevitable that in a transition this large, mistakes will be made. But I think the key thing is to get on and start, if I'm being honest, and make big change, see where we slip up, share information from one country to another, and try and do things on a European-wide, at very least, basis as well, so that we can learn in a more productive way, and so that policy drivers can actually work, which it's a challenge if you were trying to do it on an entirely just on a nation basis.
Thank you. Peter, next, you've got your hand up.
Yeah, I would definitely endorse what you said previously, and we should recall that perfect is the enemy of the good, and that's why I think we need to go forward, also to gain experience. This is a journey which we never have done before, and that's why we should also be merciful to ourselves, policymakers, that there may be mistakes done. But we have to take the step forward. I think it's absolutely very, very important, and I think through this doing by learning, I think we will of course reach good goals. Paul Monk, he mentioned it in his talk that cooperation is important. I would say this is definitely most important. In the northern part of Europe, where I come from, we collaborate very much in energy. We have a common electricity market, and we can share our assets, and it has given such a huge value to the individual countries. So more collaboration, I think, not just in Europe, but also between the superpowers that we have here around the globe. I think that's the way to go.
Thank you. Do you want to go, Christoph?
Well, since we are talking about the issue what engineering and engineers can provide, I think the evidence-based process that we are used whenever we design a product from scratch until marketability is helpful here. We are talking about this learning system, and I think it needs to be an evidence-based trial and error system with a sophisticated trial and error. But nevertheless, we need to communicate to the public that you cannot plan a transition like that from the beginning to the end without any alteration along the way.
Thank you. I think I'm going to move on to some of the other questions because we've got lots and about 5 minutes left. And I'll put this one to Eve. It's about the issue of building trust between policymakers and the public. Could you elaborate on how we might best go about doing this and what the role of engineers might be in this process?
Thanks for this. Thanks for this question. It's very important. It's concerning all of us here. I think as engineers and scientists and also economists, I think we have to really to be very clear and careful when we are speaking, discussing with citizens, with policymakers, and so on, or giving lectures, conferences to say what is known, what is not known, where are the risks. I think some communities, scientific communities or engineering communities, are minimizing the risks. Or when something wrong is happening, are not explaining clearly enough what was happening, or not recognizing some mistakes which has been done. Or that, coming back to what Christoph was saying on iteration, I fully agree, deeply agree. But doing that, it means also recognizing mistakes. Or give you an example. When we began in Europe the deregulation of electricity, we were saying developing markets will, competition will help to decrease the bills. It's exactly the contrary which has happened, these last 20 years, not only in Germany, but in France, everywhere, for other reasons, for systemic reasons that we don't have time to discuss now. So we have to recognize that and to explain that and to be modest. So
Thank you. Can I get some quick comments from Peter and Becky?
Yeah, I think one of the problems is, of course, that policy and policymakers look on very short-term issues and from maybe a siloed viewpoint, and that may sometimes cause distrust. And that's why I think it's important that we have a middleman here, an ombudsman in a way, which would be science to policy advice. I mean, think about scientists. They don't have vested interest. They as Christoph said, it's evidence-based work that we're doing. It's objective. And in that sense, in this very complex world and complex issues that we have with energy transition, I think that's where the science needs to step in as a important advisor to governments. Well, science to policy advice is not for lobbying something, but we need to replace the lobbyists in that sense with knowledge, evidence-based knowledge, and I think that would definitely improve the decisions. Also give more foresight to the policymakers, what we can expect in the future, what's the best and most efficient solutions. And let me point out that science to policy advice is not, again, lobbying money for science, but it's really to give an advice to governments, policymakers, and they will then do their decisions based on the information that they have around.
Thank you. Becky?
Yeah, I just wanted to add that I think that the National Engineering Policy Centre has supported this actually in having an independent and authoritative voice. And I think when I've spoken to industries in the last few weeks during COP, and there needs to be a change of attitude, to be honest. We need to be sharing information and sharing learning about this. We need to be tackling net zero collaboratively. This is not a competition in between industries. So we need to think differently about innovation and IP and be sharing all of that and managing this transition as a team. It's a massive challenge. Everybody can make money out of this if that is your concern, because there will be huge changes to infrastructure that are required in all of this. But we are never going to manage it if we do this in competition. It needs to be a team effort, and that's everything from power companies through to policy and regulators, through to engineering product. Everybody needs to be working together and with society to do this, not against each other.
Thank you. And I'll have a very, very quick comment from Yves.
Yeah, I know there are also fake news, and we know that we have to fight against fake news. And I think it's part of the problem we are facing to engage people to change the situation.
Thank you. I'm going to take one final question before we end the session, which is about the new German coalition government who announced an accelerated phase out by 2030 instead of 2038 for coal. With nuclear out of the picture, how can they succeed in achieving net zero while they'll have most likely to import gas and renewable energy? But that can't be sufficient, says the person who's asking the question. Any views from anyone on that? Yes, Christoph.
Well, I think that we have to realize that Germany and Europe as a whole will remain an importing region for clean energy, but hopefully clean energy. So in order to be able to really go out of coal altogether, base your own economy, our own economy on renewables, we need to start in earnest working on infrastructure, on relations, foreign relations, to import massive amounts of hydrogen and its derivatives from other countries which have a lot of sun and a lot of wind available, because in Europe we won't be able to do it on our own. And in Germany, we really need to rely on the delivery of all these objectives. So in soccer, you have a good saying, truth is lying on the pitch. So let's see.
Thank you. And someone else wanted to come in on that.
May I say friendly that I fully disagree, because it will increase the dependency of Europe. We are already very poor in energy. That is a risk that we are increasing the cost of energy, which consequence on our economy. So I'm really not convinced by the development of importation being from green hydrogen or gas. That was my comment. But we could discuss later, Christoph.
I think, Becky, you had your hand up first there.
I also disagree. I think that if we have that as a model moving forwards, that will never be levelling up of society. We need to, if you think about what that means we outsource all of our carbon emissions really to elsewhere, and that we rely on that energy, and we have a high-tech, high-energy economy that is driving technology, but we import that energy from outside. And I just can't see that. I think we need to reduce energy demand, and I think we need to look at how we generate sufficient energy to manage our own economies.
And I will give the final word to Peter.
Yeah, I think this is an interesting question, in particular in the sense that the European countries are so different. So we have our particularities, which may lead to different paths for different countries. But indeed, the German experiment, I think it's interesting in the sense that will definitely need a lot of new technologies. That would need engineers to solve intermittency questions, variability, and we will see more work on flexibility. So from the innovation point of view, definitely this huge transition that Germany is doing, that will require a lot of engineers. It is really where we need engineers, economists, and behavioral scientists to work together. And I would wish success to the German transition, and that may perhaps we could also benefit from the experiences that they definitely have.
Thank you. We will stop there because we're out of time, but thank you so much to all our speakers for such an honest discussion. And I think it's good to get some different opinions. Personally, it's nice to see that. We're going to take a short break of just under 10 minutes. So we'll reconvene for our second panel, which will be, and we'll look at how we apply some of these concepts that we've heard about this morning within the built environment sector. So please join us again at 11:25 UK time, 12:25 Central European time. So I will see you again shortly. Welcome back. I hope that you had a good break and managed to get a drink, and hope you're ready for our next panel of the day. So our first panel explored some really big ideas considering how our engineering community and education system and policy making will need to change to enable us to meet net zero. We're going to take some of those ideas and consider what they mean in practice within one very key sector, the built environment. And we'll explore how we can make sure that our homes and our workspaces and public infrastructure are moving towards being carbon neutral. So for this discussion, we are joined by 3 speakers from Ireland, France and Belgium. We've got Professor Brian Norton, who is Head of Energy Research at the Tyndall National Institute, Research Professor, University College Cork, and Professor of Solar Energy Applications at TU Dublin. Brian recently chaired the work of the European Academy Science Advisory Council that led to the major 2021 report on decarbonisation of buildings in Europe. Our second speaker is Dr. Maher Chebba, Director General at Accenta, leading the company's innovative work focusing on low carbon technology and AI solutions for buildings. And we've also got with us today Professor Lieve Helsen, Professor in Mechanical Engineering at KU Leuven, where her work focuses on optimizing thermal systems to provide low carbon services in the built and industrial environment. So to kick off, just like the last session, each of our panelists will give us a 4 or 5 minute view on the topic, and then just to let you know, speakers, if you are running out of time, I may cut you off, so please don't be offended, but I want to make sure that we have lots of time for questions, and I will leave more time for audience questions this time. So apologies if your question didn't get answered last time, but I'll try and get through all of them now. So I'll start with Brian, please.
Thank you very much, Yasmin. Yeah, decarbonisation of buildings essentially comes down to 2 things. It's reducing the energy use of buildings and then meeting the residual energy use by decarbonised sources of energy, which tends to be decarbonised electricity from renewable energy resources, or, for example, heat from district heating systems. So in simple terms, it's an easy thing to say how to do. The problem is, and this came out of the European Academy's study, is there's no single then solution on how to achieve those goals, no single silver bullet. In new buildings, there's a strong thing around new building regulation, etc., which throughout Europe has increased building standards, and indeed the achievement of highly rated buildings and net zero energy buildings or near zero energy buildings for new buildings is indeed achievable. But the challenge is new buildings are only a tiny proportion of the building stock, and it is existing buildings, the refurbishment and renovation of existing buildings, which is the major challenge, and that varies throughout Europe, and it varies throughout aspects of the building stock depending on the tenure of that stock, whether it's owner occupied, it's social housing occupied by private landlords, and there are divergences between the benefits and who pays the costs in those situations, which present barriers. Among the challenges going forward are issues to do with how buildings are rated, and I can discuss that in more detail. In terms of introducing energy storage into buildings, because they still have this problem of winter peak electricity loads and more interseasonal storage so that the overall system is more efficient. Issues to do with indoor air quality, particularly brought to the fore in our present global pandemic, where you don't want to reduce indoor air quality from a health perspective, but from an energy perspective, one seeks to reduce air change rates and have waste heat recovery, etc. So there's some optimizations there. The big issue in refurbishment of buildings is that there is energy embodied in the actual refurbishment, and so one's seeking to reduce energy consumption, CO2 emissions, but there's a whole lot of energy embodied to do that refurbishment, which is effectively paid back by the operational energy savings. But in the short term, actually energy increases. So there are issues to do with how materials are rated, but also there are design choices in terms of buildings that need to be taken. And finally, there are a whole lot of issues to do with how the refurbishment of existing buildings is actually financed to be affordable, because there is a public gain in terms of reduced CO2 emissions, my wider social gain, but there's also a private gain in terms of lower energy bills. And some of that also leads to things like rebound effects, where people might take higher comfort temperatures or greater lighting because they can now afford it. But there are other groups, and it's again varies in different localities and different countries, who spend more than 10% of their disposable income on energy, and existing energy poverty, for whom affording these particular measures is simply impossible. And often they're in rented accommodation, where the benefits don't obviously go to the landlord, who's going to pay. So there are big social issues in terms of the refurbishment of existing buildings. I'll stop there, and maybe we'll pick on some of these issues and questions.
Thank you very much, Brian. Maher, do you want to go next?
Thank you. So why buildings decarbonization is so important? So buildings, they count for 27% of the annual greenhouse gas emissions. Heating and cooling, that represent about 55% of what a building consumes, they count for 10% of the GHG emissions. So the mission is to kill about 5 billion equivalent CO2 per year, and to bring it to zero if you want to decarbonize the whole buildings. So why is that important? What's the risk? If you have a building which is not good in terms of carbon emission, it's not low in terms of carbon emission. So you have social challenges, you have legal challenges, you have exploitation challenges, you have profitability challenges as well. And you have a risk of the value of the building that you have. If it has a high carbon footprint in the future, its price will not be the same as another one, which is highly designed and sustainable. So we have worked on a solution that started at the prestigious institution called École Polytechnique in France, on a model that the scientists have developed to size and to monitor, with the help of the artificial intelligence, a building which could be low carbon based on geothermal storage. So you would take the waste heat, for example, from air conditioning, you would take the excess of solar heat during the summer, you will store it through tubes where you put fluid down to like 100 or 200 meters under the ground. And then you can recover when you need that energy. You can recover it only almost 100% during the winter when you need to heat, for example, your building. And that solution can help you cover 100% of your cooling and heating HVAC requirements. The headquarters of the Airbus in Toulouse is 100% covered by this technology. And that technology can contribute to like 93% of lower carbon, 14 times less than classical solutions, for example, that we have. Of course, there is a number of renewable technologies. So if you have a building where you have solar PV, not only solar thermal, we can size the building in a way that you have a good multi-energy renewables from solar, from geothermal storage, to cover completely the needs of the building. The solar PV will be producing clean electricity. That clean electricity is useful as well for the heat pumps. And at the same time, it's useful for lighting and for electricity. The impact of these kind of technologies, when we are talking about decarbonizing or low carbon buildings, or reducing the carbon emissions by more than 90% and having an energy efficiency of 70% in Europe, that has a huge impact on about 50% of the emissions that we have in Europe. So we should also look at acting on demand. So here what I'm talking about is producing clean energy from geothermal storage. So acting on demand means putting in place technologies where you can remotely, with the help of the artificial intelligence and machine learning, act on the heating and cooling systems, smart building energy management systems, and these could contribute to 10 to 40% energy efficiency on the building. So we need to look at both technologies, the one acting on producing a clean energy, actually producing is we are recycling wasted heat and solar abundant and putting that, storing that with geothermal storage, and acting on the demand, which contributes 10 to 40% energy efficiency. Both of them would contribute to high results in terms of energy efficiency, which could be 70 to 80%, and decarbonization about 90%. Now, I would like to let you with 7 recommendations we have put in place for scaling up and the massive low carbon buildings. First is, here we are talking about cross-sector coupling. So we need science that looks at the building architecture, building engineering systems, data, digital, artificial intelligence. We have many sectors that are involved. So sector coupling is something we need to keep in mind. Second is we need to explore best-in-class physical and software technologies that could be used for the envelope, because some people would work on the renovation of the envelope, even if the renovation of the envelope could cost 5 times more than the geothermal storage, and have 3 times less return on investment. So we need to look at the best-in-class technologies still for the envelope and still for the energy systems that we are talking about. Third, we need to be completely mindful of the fact that the data is the nerve of the war. You cannot make any diagnosis on any building to be renovated or to be improved or to be more low carbon if you don't have data on that building. So we need to work on having like a data hub, 360 degrees, which includes the consumption, weather conditions, includes some economics, and includes data that is helpful for the life cycle of the building. And then we need to work on service level agreements. Today, the buildings are static. We need to consider them as a life cycle, from the design, in construction, in renovation, in putting in place new energy systems, low carbon energy systems. We need to follow all of that through service level agreements, and then jump into outcome-based financing. A lot of people are not capable to finance these projects. So there are more and more fund managers, organizations that put in place funds that are available for financing completely these projects and get remunerated on the savings and on the decarbonization. We call it outcome-based finance. And finally, scaling up means that we need to look at 2 dimensions. Either buildings sitting into a district at a geography where are close to each other, typically a campus of a university where you have 30 buildings, or a district where you have several buildings that share the same land. And we need also to look at the organizations that have a diffuse fleet of buildings. You take a postal company in France or in many other countries, they have 10,000 buildings. They have millions of square meters. These ones who need to decarbonize their buildings, they need to have a view, diffuse, consolidated at the top level, exactly as you consolidate your finance or P&L, you need to consolidate also your emissions at the top level. So there are solutions that are capable to do both, look at the geography or eco-districts, for example, side, and also looking at consolidating buildings that are diffused across the whole territory. Thank you.
Thank you very much. And over to you, Lieve, please.
Thanks, Yasmin. I would like to start by stressing the urgency in the built environment. Given the lifetime of technologies installed, action is needed now, today. And we all know that technologies exist and the trends are clear as well. We move on the one hand towards electrification by using heat pumps, but also towards collective approaches by using thermal networks. Of course, we have to make a distinction between renovation and new buildings for sure, but for both categories, system integration is key. So my first statement is it's time to move from a technology readiness level, a TRL, towards a system readiness level, an SRL. And let's start with renovation, which represents the biggest market share. We should aim for an optimal combination of the building envelope and the energy system. So using the full potential of the building to reduce demand and fit this to the HVAC system and the controller, and thereby progressively increasing the share of renewable and residual energy sources, not only to mitigate climate change, but also to improve the air quality and autonomy. Now, when the budget is limited, which is usually the case, then, and the full house option, let's call it, is not feasible, then future-proof design and flexibility should be points of attention. So typically hybrid systems where less efficient or fossil-based technologies keep a minor part, they can deliver the major part based on the renewable energy sources and in a cost-effective way. Now, which systems have to be installed? That's a big question. And to compare different alternatives, dynamic simulations are needed. And this represents an extra engineering cost. So my second statement is a cost-optimal design fee is only that one that leads to a cost-optimal project, where cost includes all externalities. So we have to care for people and planet as well. Now, maximum integration of renewable and residual energy sources requires low-energy systems and hybrid systems. And dynamic simulations allow a correct evaluation of hybrid system concepts and their control, which both can have a huge impact not only on the energy we need, but also on the power we need, and thus on the global system performance and the total cost of ownership. Now, since it's not easy to realize that 100% renewable energy sources based on individual building level in a cost-effective way, we have to look further in space and time. And by moving towards smartly controlled collective systems, a synergy can be exploited. And then the question is, at which scale do we have to look? In Belgium, we are not that collective thinking yet. So there, maybe we have to start from very tiny clusters, for example, 3 neighbors that share their energy system, and then gradually moving to larger neighborhoods where system integration becomes then a real challenge in both operation and design optimization. And taking into account the current trends towards electrification, smart grids, exploitation of flexibility, I come to my third statement, which is buildings have a role to play in the global energy system. Now, if we move to new buildings, it's clear that design has much more degrees of freedom, and system integration can be realized over timescales, over technologies, multiple buildings, sectors, and thereby including the local context. And a nice example here is the hybrid geotapes concept. Within the hybrid geotapes concept, a heat pump is used. So there we introduce energy efficiency and electrification. The source is typically a bore field, but depending on the local context, it can also be an aquifer, a sewer, or something else. This is renewable energy source, and this allows for seasonal energy storage and also for direct cooling. At the building site, the heat pump feeds then taps. Taps are thermally activated building structures, and they are a low exergy heat and cold emission system, and they represent a short-term storage. So they allow the interaction with the smart grids through demand response actions. Now, since each building deserves a geotap system and architects need their design freedom, we add a fast reacting secondary system to cope with fast disturbances. So we result in a hybrid system, and that needs smart control. White box model predictive control is then the whole system integrator, where we can optimize towards minimum carbon dioxide emission, maximum share of renewable energy sources, or minimum energy use or cost. So hybrid geotaps is a very strong concept for climate neutral comfort supply, where MPC is the system integrator, and MPC can improve comfort and at the same time lead to energy savings up to 40%, as we have shown in demonstration sites. So I would like to conclude with my final statement. In hybrid systems, design and control are challenges, but both influence each other, and this can be maximally exploited towards a cost-effective synergy on building level and on cluster level. Thank you.
Thank you very much, everybody. I'm going to start with a question that's come in through the Q&A. And just again, to remind everyone watching, please do submit your questions at the bottom of the screen. So everyone is talking about making the building environment sustainable. What about the carbon footprint of creating the building in the first place? How do we use less steel and concrete, which are very high carbon? Who would like to take that first?
Maybe I'll start. It is, as I said, an important issue to look at the embodied energy of buildings. And one thing is actually to focus on refurbishing rather than building new buildings and see if you can actually reutilize buildings. But it comes deeper than that in terms of actually designing the components of a building so that they are available not just for recycling but actual reuse. So design for reuse, designing systems so that the components that are most likely to fail, and things do fail inevitably, but you can predict the failure of things, and the components that are most likely to fail are designed to be replaced. So there's a whole set of issues around that sort of circular economy to minimize that impact, and using much more of the materials that have high energy content because they're production processes are essentially available for reuse at the minimum would be the key challenge.
Thank you. Maher, did you want to comment?
Yeah, absolutely. So the whole life cycle of the building counts, and everything that you need when you are at the construction level and even at the renovation level. On the envelope, you have a number of materials that you use that have a carbon footprint, and all the models that are the true ones or the most accurate ones include everything in the carbon footprint, in the material you use for the envelope, in the emissions of the building as well, with the energy system that you have in place, the gas. If you have gas boilers, you will also calculate the gas boilers and so on. Now, cement industry contributes to 15% emissions in the world. This is a huge, okay? And if you take a company like Lafarge Holcim, they have a whole team working on reducing their emissions with new types of materials, for example, that could be used. If you take a company like Vinci is a construction company. They have now a kind of an envelope they put on the surface of the buildings that integrate what we call BIPV, building integration PVs as well, that are in the same time producing electricity. All of that is calculated in the emissions. And this is why what I said is we have to look at the investments. If you have, for example, 60 euros to spend for the British pounds, then where would you spend it and what's the best return? Would you spend it on an envelope that costs a lot of money and then gives you some return, for example, maximum 30 or 40% energy efficiency, or would you spend it on the energy system that would cost 5 times less and give you 3 times more return on investment because you can have 70% energy efficiency and 90% decarbonization. All of that is calculated with Excel sheets simply. And then you can get to the best result just on calculating and putting everything. You should not have any hidden cost or hidden footprint of CO2, and the models are good today.
Thank you. And Liva, did you want to comment on that question?
Maybe very shortly. I agree that you have to look at an holistic approach, that you have the complete life cycle cost for the whole system. But I also want to stress that you have to match the building with the energy system. That it's not just choosing the building envelope and choosing an energy system and then, okay, they just have to work together. They really have to be matched. So I think that's important as well.
Yeah, just to say, there have been calls, for example, from the Green Deal around the whole matching actually of the building construction or renovation and the energy systems. We have been working with like 20 partners to make that match, construction ones, energy systems ones, digital companies as well, companies that are specialized like Viscap, for example, into calculating the overall life cycle of carbon emissions for a building. And the objective was to make all that match to reach out at the end, less cost on the construction side or innovation side, less energy consumption and less CO2 footprint, all combined and all integrated in the new approach. Today, they are not integrated. You are right.
Yeah, I think we did talk quite a bit about collaboration in the earlier session, so that comes into here as well. I'll take another audience question. The carbon emissions of buildings are being noted in discussion, but these are usually modelled and often using quite simple models, and for example, EPCs. How can we use real data to inform our decisions on carbon reduction and do so at scale? And I think maybe, all right, go to Brian first.
I'm happy for someone else to go if you wish.
I was going to go to Maher, just from the kind of AI perspective, but you go first, Brian.
Okay, I'll
give him a chance to think.
Yeah, well, as I started, I mean, it is a very important area because a whole lot of national policies are based on supposed national energy consumptions of buildings, and yet no country actually measures the energy consumption of all their buildings. So those numbers are actually based on EPCs, energy performance certificates, and they are a rating of a building for a defined type of construction, occupancy, heating system, etc. And they are not designed to correspond to actual energy use for each individual building. Now, the theory is they do in aggregate, but many studies have shown that's not actually the case, and it's not actually the case for older buildings. And that leads to a whole lot of issues to do with the effectiveness of policies when they're actually introduced, interventions when they're actually introduced, and also the expectations of policymakers as to what energy savings that might actually occur when you make certain interventions globally. And that's further compounded by the fact that buildings are not systems, they're not energy systems, they're systems for people to be in comfort and health. So the objective is people, and people rather than energy. And if you insulate a building, for example, people will take higher comfort temperatures. If you have low energy lighting, and modern LED lighting, for example, uses a fifth of the energy of an incandescent bulb, but you tend to have more than 5 times of them. So you've got more lighting energy, and those things need to be factored in as realities rather than inconveniences into the process. So, picking up the point that Lieve made, I think a big thing is to have much more detailed simulations of entire stocks, so that and validating those simulations with comparison with actual measurements, and then a whole lot of other things using AI, which others could talk about, around how you use that data effectively.
Thank you.
Yeah, I mean, today, as I said, the nerve of the war is the data. We spend much more time into collecting the data and knowing what is the baseline of the current building, what is the building consuming, where is the building consuming, in the lighting, in the electricity, in the heating, and so on. And if you don't have the meters in place, well placed, all the sensors in place, and you do not have all the detailed data that can help you make the transformation properly. So the starting point is to make a diagnosis, collect data. If the data is not available, is to put sensors and to collect that data through sensors. And then you have also international references like the IPMVP, International Performance Measurement and Verification Protocol, that helps you comparing apples with apples. So the current referential, for example, when you measure it with the IPMVP, you know afterwards, you know, what does it mean to improve it and to have 20% energy efficiency on it or 50%, and compare on a yearly basis how much improvement you have been making. Okay, so today when we make the calculations regarding the CO2, we know exactly the carbon emissions for the gas. We know exactly the carbon emissions that are calculated country per country from the electricity. In France, the majority of electricity is clean because it comes from nuclear. In China, that would be a different story. So we calculate that properly as well. And then if somebody has also a plan to change gas by biogas, we know also that the biogas has like 70% less carbonization than a normal gas, even if the price is higher. All of that is calculated in our economic calculations to say, what does it mean if I do that project in terms of transforming an existing situation with its referential to something which is better and more energy efficient. One KPI is the energy efficiency. Second one is decarbonization. Third one is the cost. And the last one, which was mentioned by Brian, is the well-being. It's very easy to have an energy efficiency or reduce energy consumption if people, you know, get a bit colder, but we don't want them to be colder. We want them to be at the same comfort. So at equal comfort. So the well-being is part of the story as well. And that's an important KPI beside all the 3 KPIs I mentioned before.
Thank you. And Liva, did you want to comment on this question?
I would say it's the core KPI. I think we do not build to use energy. We build to give a comfortable indoor climate. That's the main reason for buildings. Now, I want to stress indeed that measured data are extremely important. But what we in research encounter is when we test, for example, our advanced controllers in the real buildings, that the data we gather, they are often corrupt, or we have missing data. So the whole story on big data, I'm really willing to believe that's the way to go, but then we have to do something on the way the sensors are installed or the quality of the sensors, because what we now see is that a lot of rubbish comes out, and that's not something you can build on. So this is really a difficult point today still. We are not yet there, I would say.
Thank you. I've got a sort of related question. In the last session, we talked quite a lot about behaviour change and how we bring everyone that's involved in the energy transition along with us and engage the public. And I think that obviously applies quite a lot here, as you've all just said. How do you think we can deal with this as engineers?
Yeah, I mean, in the behavior change, it depends about whom we are talking. I mean, if you are talking about users and asking the users to be smarter, this is what I heard, for example, when we co-founded the Smart Grids in 2005, people were saying we need to have smart users. No, that means we failed. If we need the user to be thinking about everything every day, we need the technology to help the users by sending awareness, by sending alerts, by doing a lot of things that are automatic or semi-automatic, that we get to the results that we want to achieve. But we should not just consider that the users have to be absolutely smarter to be successful. Then the other behavior is the way we consider the real estate of buildings today. Today, you have the ones who build the buildings and they don't care about what happens afterwards. You don't have any life cycle. You have people who exploit the buildings who are different from the ones who build them. So you have everybody like is giving the hot potato to somebody else, and take care. It's out of my business. We need to change that. We need also to make sure that all the ones who provide numbers and say, yeah, no worry, I will get your data, I will put my technology, you will get 20%, and at the end, you don't observe 20% energy efficiency. They have been bullshitting you. So you need to have a skin in the game. You need to have people who really present technology solutions, provide economics, and take commitment on the performance. There are contracts for which there are subsidies. If you have a commitments on performance and decarbonization, you get the subsidies related from the government to that. It's what we call in France certificat d'économie d'énergie, for example. And if you don't get to that commitment on the performance, you don't get them, or you get much less than the ones that you ask for. So these are the things we need to put in place. And the last point is the financing. Yes, to make transformation, you require a CapEx, and then you have an OpEx. To get an OpEx which is cheaper, which is better, and so on, because you have put in a certain technology in place, you need to invest sometimes more. We need to simplify the financing models and make that like a common practice in public as much as in private. So traditionally, you can do it in private, for example, but not in public. So we need to have that in place in both. And then allow that, between the first time where somebody says to you, I want to decarbonize my building, and the time you start the project and you get it live, you should shorten that time to a maximum by having these standard models of financing and get remunerated on the savings.
Thank you. I'll come to you next, Liva, because you've made the quite a good point that we build buildings for people's well-being. So I don't know if you have any views on behaviour change or how we engage the people in those buildings in this.
Yeah, it's a difficult one for engineers, I think. So I would rather put a warm call to collaborate with human sciences, because I think we as engineers, we will not solve the whole problem there. We really need that expertise as well. And then we can develop technology that makes that it's like almost automatically done. That as first we need to know the preferences of the user and how the acceptance can be increased and so on, and then we can adjust the technology such that the users themselves do not have to be concerned about it, that it's just going on and yeah, in a quite automated way. I think that's important.
Thank you. Brian, did you have any?
Yeah, I think the problem with the built environment behavioral change is whose behavior. And we tend to think maybe the responsibility of building occupants, but the behavior of builders, that how they build buildings. For example, there's a tendency in some jurisdictions to build new buildings, or indeed where there are standards in place, refurbished buildings, to the minimum standard. And yet there is very little cost penalty in building beyond that, for example. So there is behavior there. Often people are in social housing or private tenanted housing, and it's the behavior of the landlord in terms of their responsibility, etc., that needs to be developed. Underpinning this is, I think, a more fundamental issue of the public and private benefits, in that there's a public benefit in reducing CO2 emissions, in security of supply of energy use, etc., which has to be taken, I think, as a collective burden on society, and then provides the incentives that create a different playing field for private behaviour. Also, more fundamentally, and at the building physics level, but one of the challenges with low energy buildings is actually in many climates they overheat in summer. It's very easy to develop a building which is energy efficient from a heating perspective, but you've got an overheating problem. You've seen that then arising major problems of mortality due to overheating of buildings in the summer. The solution to that is that building fabric elements, building facade elements become more adaptive to climate. So there's not just one point of equilibrium, in the year, and then either end of that you need heating and cooling, and that then gives the occupants of a building more opportunity to adapt their building to the climate. And I think the opportunities for people to modify their behaviour in terms of the operational use of buildings are limited at present. So there's a lot of dimensions to that question.
Thank you. Let's take another one from the audience. I think we've talked a little bit about this already, but could we have your views on whole life carbon assessment in the built environment? Is this a useful step to understand our current emissions and help guide us to a decarbonised building sector? And what else should we be doing? Liva?
I would like to make a main comment in the sense that we often talk about carbon and carbon dioxide and sometimes greenhouse gas emissions, but there are much more pollutants than that. So I think local pollution is maybe as important as global climate change is, and we should consider them all. I think if we go to a life cycle analysis, life cycle cost, we should include all ways of environmental pollution and not only climate change. I think it's an important challenge and we have to go in that direction, but we should not forget the other things. And I think good databases are important to rely on to get all these calculations, and I think, yeah, it's the way to go to make this holistic approach. Yeah.
Thank you. Brian, did you have a comment?
Well, I would agree totally with what Liva said. I think the important thing is not just to do that assessment, but actually build it right back ab initio into the design process, whether that's a new build or refurbishment, etc., as part of the design process, because it's not just materials choices, but actual design choices. We don't have time to go into detailed examples, but there are design choices which can lead with exactly the same operational and energy saving, operational reductions in pollution, but have much less embodied energy and much less local environmental impact.
And Maher, did you want to make a quick comment on this one?
The air quality is more and more requested together with the request about the energy efficiency and decarbonization. And this is why, for example, Axanta has been acquiring recently a company that includes air quality, for example, in their solution. We work also with a partner in China, which is a joint venture with between RN and Aden Group. And in China, they have developed also a platform together with the energy efficiency, which includes, of course, air quality, which is an important topic there in terms of pollution. Same for India.
Thank you. There is a question which I think is off the back of the work you described, Liva. Are there plans to extract heat from the heated waters in the sewers downstream of the buildings?
Yes, there are plans to do that. Indeed, we are looking how can we use the local context as much as possible and as good as possible, because not only extract things for our use, but also safeguard the nature itself. We should not harm these local resources, and how can we include them as much as possible into our global system approach to heat, cool, and ventilate buildings, and make it happen across the borders of one building. So usually this encounters the infrastructure of a thermal network, and often it's just a low temperature thermal network where we just use the temperatures as they are available in nature, and we upgrade them at the location where we need the heat up to the temperature level we need. As such, we can have a very good match in what we then call exergy instead of energy. Yeah.
Thank you. And is that something you've come across in France or in Ireland at all?
This is a fantastic opportunity. We traditionally use for the geothermal storage the waste heat coming from air conditioning and excess from solar. We believe this is also another opportunity for what we need to store at a certain temperature at 100 or 200 meters, where we need like 12 degrees. And that's really a fantastic opportunity as well to get the thermal storage and to use it when we need it.
I think this is all part of a wider agenda of sort of intersector coupling, of matching your energy sources to your energy needs. I don't think there's waste heat recovery in that context in Ireland at present, but there is, for example, projects where district heating is using the waste heat from data centers, for example. And that idea of looking at proximity and looking at from a systems perspective, and looking at the opportunities for intersector coupling both with heat, electricity, etc., is, I think, crucial for the future.
Perfect. Yes, Liva.
Maybe to mention that it's not all I would say very easy to implement, because the main challenge in that system is the heat exchanger. It's fault immediately. So you need systems, you need innovation on the component level that cope with this. But energy-wise, it's a good solution.
But this is why it's important to look at things in a holistic way. If we work in silos, take the example of electricity and heating, for example. If you take the electricity side separately and the electricity storage separately from the thermal storage, for example, you might not be optimal here. So you have to put it together and then work on the storage both sides, flexibility thermal as well and flexibility electric as well, and make them all work together.
Thank you. I'm afraid we're, oh, sorry, Liva, I think we can have one final comment, but we are out of time.
Yeah, I'll make it short. I have the feeling that we see that a lot of technology exists, and it's the main challenge today is putting everything together and let it work together in a good way, in an optimal way. And there often funding agencies feel like this is not innovative. So if you want to apply for funding for that type of research, they say it's just combining things that exist. What's new? And I think they feel like everything is there, but making it work together, it is quite a challenge still today, and that is not yet solved if we go across sectors and so on. So there is still some work to do there, and maybe we should stress that a bit more, because policymakers often think it's all there, and there is still a lot to do.
Yeah, if you look at the Green Deal Innovation Fund, where the European Investment Bank has put some money to fund decarbonization, big industrial decarbonization projects, they consider that putting things together and the integration as innovative, even if every component of that system is not innovative, but the assembly of all of them, they consider it innovative, should be around TRL 9 to be eligible for a Green Deal Innovation Fund, whether it's large scale or small scale. So you are absolutely right.
Yeah, but then you talk again about a TRL 9. I really want to push to go to an SRL. We really have to go that whole chain as well. We are indeed at the higher end of the TRL, but the SRL, we are still very low level.
So they still use TRL as a terminology, but they consider the system to be innovative overall. So they don't call it SRL because that's not a terminology commonly used, but they accept that people come and have plenty of like electrolyzer and plenty of things that are available at that work, but they have never been integrated all together as being an innovation. And in this case, they say it's fine, then let's put a good score also for the innovation on that project. Sorry, Yasmin, for taking more time.
No, it's a good point to end on. I think it ties into a lot of the stuff that we were talking about in the earlier sessions around collaboration and systems thinking. So thank you very much to all of you. We will. That's the end of the session for this morning. There's lots of us to consider over the lunch break. So I would like to thank all of the speakers who have been with us over the course of the 2 sessions this morning for the really insightful contributions that they've given us on these topics. Our session for the morning focused on Our sessions this morning, focused on a topic that's widely acknowledged as the cornerstone of Building Back Better. Following our recent COP conference, we are well aware of the urgency of building a more sustainable future. And I think we've had a brilliant discussion this morning about what that could look like in practice and how we as the engineering community can help to deliver it. This afternoon, we are going to be exploring a slightly different topic, which is perhaps less prominent in our news and social media, but very essential to delivering a more sustainable future. And that is all about how we build resilience in our complex and interdependent systems and in the world. So please join us again for that session. We will be starting again at 1:45 UK time, which is 2:45 Central European time. In the meantime, I hope you enjoy your lunch break and get a chance to get some food and hopefully step away from your computers and maybe get outside if it's nice and sunny outside. So please be ready to join us again at 1:45 GMT. I will see you then.
Thanks a lot, Yasmin.